Imagine you slipped over the edge of a spacecraft and fell straight into a black hole. Would the intense forces kill you instantly, or could you actually survive the plunge? The truth is, you wouldn't die right away. Despite what science fiction suggests, a black hole does not act like a giant cosmic vacuum cleaner, actively sucking up everything in the neighborhood. If you are millions of kilometers away, it behaves exactly like any normal star or planet with the same mass. You could theoretically orbit it safely forever. The danger only kicks in when your trajectory takes you too close. At that proximity, the gravitational pull becomes incredibly intense. Your fall guarantees a one-way journey toward a point where every known law of physics completely breaks down. As you drift closer to the black hole, you cross into regions where the fabric of space-time itself is heavily distorted. This diagram shows two synchronized clocks to illustrate a concept called time dilation. As the gravitational pull grows exponentially stronger, the physical passage of time for the clock deep in the gravity well actually slows down. To understand what this means for you, we have to think about someone watching from Earth, safely removed from the gravitational distortion. To that distant observer, your fall wouldn't look fast. They would see your final moments stretch endlessly, until your image eventually appeared to freeze completely in place. But from your perspective inside the spacesuit, you wouldn't notice any slowdown at all. Your watch would tick away at its usual pace, and time would feel perfectly normal. Time ceases to be a shared, universal constant. This is the first major failure of human intuition you experience as you fall deeper into the void. Getting closer to the event horizon, the effects of gravity shift from warping time to violently distorting physical space. This diagram illustrates spaghettification. The black hole's gravity pulls significantly harder on the bottom of the spacecraft than the top, causing it to be vertically stretched and horizontally compressed. Falling into a small black hole, this severe difference would tear your spacecraft apart before reaching the event horizon. However, around a supermassive black hole, the gravity gradient is much smoother. The physical stretching is minimal, allowing an astronaut to cross the event horizon completely intact. This crossing is surprisingly calm. There is no violent shockwave and no glowing wall of fire marking the boundary. Passing the ultimate point of no return happens in complete silence. The trap simply shuts behind you, and escape becomes physically impossible without you even feeling it. Now fully inside the black hole, you are cut off from the observable universe. You have entered uncharted territory. Once you pass that threshold, science goes blind. Humanity literally does not know what happens to you next. Our rules for the macro-scale universe, governed by Einstein's theory of general relativity, predict one specific, crushing outcome for the interior. But our rules for the microscale universe, governed by quantum physics, hint at a completely different and conflicting reality. Deep at the center, these two foundational pillars of science violently clash. All of our human equations break down, producing impossible, contradictory answers. So you won't survive the fall, but the journey reveals the black hole's true nature. It is the universe's ultimate fault. It remains the one place where nature still hides its most profound mysteries, perfectly shielded from human math.